Welcome back. All right, now we're going to still talk about the semantic science, and now we're going to talk about hypotheses. So hypothesis is just a program that makes predictions on data. We'll see this before we we see probabilistic programs. And so to be useful for decision making, predictions should be probabilistic, and that makes distinctions the idea of probabilistic programs. So that's a hypothesis, it's just a program that makes predictions on data. It can be a simple program like a neural network that makes a prediction, or it can be more complicated and it can be arbitrary probabilistic prediction. Okay, so what we're going to mean here is it's just a program that makes predictions on data. So in fact, in our landslide deposits, here is a very discretized someone predicted a model about where they'd find landslides, and the black outlines here, these other ones, were actually observed landslides around the predictions. All right, so now let's talk about how to do probabilistic ones. So now we have random variables and we have triples. So let's try and talk about that. So we have random variables of probability theory and individuals, classes, and properties of modern ontology. Okay, so now what we need to do is need a definition. We're going to define a property R is functional, means if x is related to y1 and x is related to y2, then y1 is equal to y2. For example, the height of a person, if you define it well enough, so you talk about when it's taken, it's functional. Someone only has one height. Someone has only one topmost degree. Someone has their eldest, their parent is functional. So if you only have one parent, okay. So now what's going to do is not all properties are functional. We're just going to treat functional properties differently. So for functional properties, there's a random variable for each individual property pair. And the range of the random variable is the range of the property. So if height is functional and building 17 is the height is a random variable, and its domain might be the real numbers. Okay, so it might be the height in meters. So typically here what we're going to do is we're going to put the object, the individual and property, as a pair. We're going to make that into a random variable. And for non-functional properties, there's a Boolean random variable for each individual property value triple. So if a building was restored a number of different years, we might have building 17, year restored 1988 might be true or false. Whether it was restored in 1989 is another Boolean random variables, and so on. So there's a Boolean random variable. Okay, so that's what we're going to do is we'd have individual property pairs or individual property value triples. And the reason we can do individual property pairs, it has a unique value, and that's what functional gives us. So each individual property has a unique value, so it can become a random variable. So now we have Aristotelian definitions. We said an apartment building is a residential building, the number of units is many, and the ownership is rental. So now we can, because we know this, we now know the probability that something is a building is the probability that its type is a residential building, because it needs this, and it needs the number of units as many, given it's a residential building, and it needs its ownership, its rental, given the number of units as many, and as a type residential building. Okay, so what we're going to do here is we're going to have this conjunction of things, and that's the definition of apartment buildings. Notice something peculiar going on here is that we're going to make it so that we don't necessarily, number of units is many, is not defined for things that are not residential buildings. So in some sense we have this conjunction is not commutative. So we want this and this and this, but we want this, if this is false, the number of units is many. So we're going to worry about those things. Okay, so that's how we're going to use Aristotelian definition. Aristotelian definitions are going to correspond to random variables when we have a particular object, and they're going to give this definition. So in some sense, we've reduced classes to properties and property values, and now property values become random variables. And that's how we're going to introduce classes together with probability theory. All right. So now let's talk about how semantic science will work, this idea of having people publishing hypotheses that we can then use. So it turns out the governments are publishing data with rich ontologies already. The journals are forcing authors to publish data. So one of the interesting examples, the European Union is mandating that all levels of government in the EU provide all spatial data using standardized vocabulary. And this Inspire standard is at the end of next year, in the end of 2021, all levels of government across the EU will be forced to publish all of their data with respect to these Inspire standards. And so there's a whole lot of interesting real-world data that's now being put forth, and now there's a great opportunity for doing this. And in some sense, it's like in computer vision, when we had at one stage every camera had its own format, and that was really hard to build vision recognition systems. But now we're having standardized formats for cameras. All the cameras essentially use the same format. We can build programs that exploit that data, because now there's lots of data about it. And similarly, it's going to happen with things like Inspire, as people are starting to publish more and more data with respect to ontologies. And the idea we're going to do is to also publish hypotheses that make predictions. And these have to interact with this standardized vocabulary. So here's the diagram we saw before. Ontologies represent the meaning of symbols. Observational data is published. Hypotheses make predictions on data. And data is used to evaluate hypotheses. And hypotheses are used for predictions in new cases. And all of these evolve in time. So here's the sort of thing we might want to do is semantic science search engine. And this is actually something we can't do at the moment. Given a hypothesis, you'll find about data about what it makes predictions about. So I have a hypothesis about landslides. I should say, how well does it work? I might have a hypothesis about how to protect people from COVID-19. I'd like to say, what data is there about this, and does my hypothesis fit the data? Okay. Then given a data set, I'd like to find hypotheses about which make predictions on the data set. So I'd like to evaluate hypotheses. And then given a new problem, I'd like to find a best model, where a model here is a whole lot of hypotheses that together fit together to make a hypothesis. Has an interesting dynamic, and we're going to talk about that in a minute. More about that in a minute. So the idea is the dynamics is that new data and hypotheses are continually added. So in some sense, what we're going to do is we're going to have data and hypotheses are always going to be published. In some sense, it's like machine learning, except there's no test data. The test data are always trying to predict new data. And because when people publish new data, they're going to say, who's prepared to make a hypothesis about this? And you can evaluate all existing hypotheses. So you always want to predict tomorrow's stock exchange, or what's going to happen tomorrow in the coronavirus, and not predict yesterday's or anything random in the past. Turns out predicting tomorrow's is more useful. It also means it's harder to cheat. It's harder to sort of go back and look at tomorrow's data, because you have to publish a hypothesis that makes a prediction, and when the data comes out, we can evaluate your hypothesis and see what it predicted. All right. Now, anyone can design ontologies. They're not built in. So at one stage, people thought we should mandate ontologies of things. But what's happening in this semantic science is like the semantic web, is people just vote with their feet what ontologies they use. What I mean by that is that people just use whichever one they want, and the most popular ones will probably survive. And the need for semantic interoperability, the fact we want to have consistent naming of things, will lead to ontologies with mappings between them. And that's the hope anyway. So then ontologies evolve with hypotheses. So a hypothesis might invent a new useful distinction. They're often called latent features. And they become words. And we can add users to words. We'd add these to the ontology, and other researchers can refer to them, and then you reinterpret the data. So almost all of medicine is made of latent, what were once latent features. The idea of a bacteria, the idea of an atom, is all latent features that we don't actually observe. We just hypothesize that they're there, and we hypothesize we're there, and when we find them, we can explain why we get this particular view in a microscope. Is going to explain by the fact that there is a virus there. Okay, so hypotheses, that's how language evolves and ontologies evolve. And now ontologies are judged by the predictions of the hypotheses that use them. So the role of vocabulary is to use useful distinctions. Okay. Now I want to know what the following two have in problems. So between 1976, people put up all of this measurement equipment to measure the level of ozone in the atmosphere all around the world. And around 1985, they tried to look at the data for the Antarctica, and they discovered that every observation was rejected because it was out of range. So it turned out the amount of ozone in the atmosphere was so much less than they'd ever anticipated that they kept saying, nope, this is out of range, so we're going to reject this hypothesis. We're going to reject this data. So every piece of data between 1976 and 1985 was rejected because it was out of range. Another problem is this robot kidnap problem. So in here, there was people doing pathfinding for robots. They had to find themselves, find out where they were, and locate themselves and get to a particular destination. And the trick that people did was that in this robot competition, they put a bag over the top of the robot and they moved it to somewhere else at random and took the bag off, and they just tried to decide whether the robot could find itself again. So this was a problem in the AAAI conference, I think. So it's called the robot kidnap problem. Okay, think about that, and we'll start, and I'll tell you in the next lecture, the next part of this.